Okay, so in this series of videos, we're going to be taking a look further into oscillations, and we're going to be treating damping today. Ooh, we don't want green. Be treating damping today. So we can imagine a situation here. Let's say I've got a mass on a spring, like so. Um, let's say at the moment it's over to the right of equilibrium, and let's say at the moment it's moving to the right. Okay, if we go ahead and draw a free body diagram for this, and we can neglect the vertical forces, we'll have a restoring force from the spring trying to pull it back, minus kx. Remember that minus is already baking the direction into the cake for us. And in this particular case here, the force of the drag, minus cx dot, is also going to be pointing to the left, but that's just because in this particular case x dot is pointing to the right. If the object were, say, moving to the left, then even if it were over to the right side, that would force the drag force to be pointing to the left. So these aren't necessarily parallel. Anti-parallel will happen for half of the cycle time. Okay. In any case, we can go ahead and write Newton's second law for this. So mx double dot equals minus kx minus cx dot. All right, so let's work to gain this into standard form. So that would be mx double dot plus k, oops, we want standard form, plus cx dot plus kx equals 0, and it's not quite standard form yet because we have a coefficient from the x double dot, so let's divide through by the m. We get x double dot plus c over m x dot plus k over m x equals 0. Well, the first thing that you can pull out of this is that, unlike before, the solutions are not going to just be sines and cosines. That can't happen. Because, for instance, if this is a sine, great, that's negative sine, they'll cancel, but then that would make this cosine, and that cancels against nothing. So we're going to have to find some other solution. The trick we can do is remember that a lot of times in math class I'll introduce the derivative operator d, which is just simply another way of writing d dt for us. And by using this operator notation, we can rewrite the differential equation as d squared plus c over m d plus k over m, all operate on x equals 0. Now, in general, this is only going to give us a solution if the thing in the brackets is identically 0. So the next step here will be to treat this like it was a quadratic equation and solve it. So we'll try to go ahead and factor it. Now, the first bit here to keep in mind is that this bit right here is our old friend omega naught squared. So let's go ahead and identify that. Similarly here, since we're going to be treating this like it's a quadratic, we want this to look like a cross term. So you remember the cross term, this should be 2 times something. So we'll decree that that is 2 gamma, like that. So then that makes our equation now d squared plus 2 gamma d plus omega naught squared operating on x equals 0. And in general, that's only true if the stuff inside the brackets is 0. So we'll work on making that happen. All right, so that's going to give us we require d squared plus 2 gamma d plus omega naught squared to be equal to 0. The only way I know how to solve this is to complete the square, so let's go ahead and start doing that. So we'll have d squared plus 2 gamma d, then we had the stuff we don't like, we move over there as, oops, we need to leave a little bit of space here. Take the stuff we don't like, and we put minus omega naught squared over there. And then we put the stuff we do like over here, since this is a 2 gamma cross term that forces that to be gamma squared. Then I have to add it to both sides to make it happen, and I've completed the square. Okay, so that means that this is equal to d plus gamma squared. And so it's equal to gamma squared minus omega naught squared. And so our solutions are that d plus gamma can be equal to either plus or minus the square root of gamma squared minus omega naught squared. All right, I don't want to write that radical anymore, so let's give that radical a name. We'll call it q for the moment. All right, so that gives us d plus gamma equals plus or minus q. So finally, that gives us our our relations that d plus either d plus gamma plus q is equal to 0, or d plus gamma minus q is equal to 0. So definitely, since one or the other of these is equal to 0, the product is definitely 0. And then we can go ahead and go back into operator land and operate this combination on x and demand that it be 0. Okay, so this means that we can now go ahead and separate the equation. So separating, the first one we can try is d plus gamma plus q operating on x equals 0. Okay, so general rule of thumb in physics is if you don't know what the solution is, guess a decaying exponential. That's probably a good guess. So we will try here for case 1 a trial solution of x1 equals some coefficient a1 e to the minus alpha 1 t. Okay, so we go ahead and stick that into here. When I differentiate this, it's going to bring down to minus alpha 1. So I'm going to get minus a1 alpha 1 e to the minus alpha 1 t plus, oh, I'm sorry, I wanted to separate the negative 1 first, plus gamma minus q operating on a1 e to the minus alpha 1 t, and we demand that that be equal to 0. Well, the only way that that's going to be 0 is if our alpha 1 is equal to gamma minus q. Similarly, if we pull out the case of d plus gamma plus q, sorry about that, operate on x equals 0, we will try trial solution x2 equals a2 e to the minus alpha 2t, and it'll work too as long as alpha 2 is equal to gamma plus q. All right, So the complete solution is going to be a linear combination of these two separated solutions. So x of t will be equal to some a1 e to the minus gamma minus q t plus a2 e to the minus gamma plus q t. Well, that's all well and good. So now we gotta think about what the solution actually looks like. Now, it'll be helpful for us to recall that Q is equal to the square root of gamma squared minus omega naught squared. So there are a total of 3 possibilities that we can have here. Possibility number 1 is that gamma squared could be bigger than omega naught squared. If that's the case, then Q is greater than 0. We call that overdamping. All right. Possibility 2 is that they're equal. In that case, Q is equal to 0, and we say it's critical damping. And then finally, we have the possibility that gamma squared is less than omega naught squared, which means that Q could be imaginary. And we call that underdamping. All right, so let's take a look at these cases in turn. So let's go first, case 1, the overdamping. All right, so our solution is of the form a1 e to the minus gamma minus qt plus a2 e to the minus gamma plus q t. All right, so we've got a combination of 2 decaying exponentials that are going to add together. So if I plot it as a function of time, I'm going to get something looking sort of like that. Now the way I like to think about it is you can see here at first it's getting faster and faster and faster as it's heading back to the equilibrium position, and then it tails down. So here the spring is playing a greater role, so I'll say the spring wins. Spring is playing a greater role than the damping forces, and so it's making it go faster towards the center. And then here, this is where the damping wins. The spring is still successfully trying to restore it to equilibrium, but the damping is slowing it down, and so we asymptotically approach the equilibrium position. Okay. Case 2 is critical damping. Now, what's going on here? Well, we've got a little bit of an issue here. So here, Q is equal to 0. So that means that When I put in q being 0, my solution is a1 e to the minus gamma t plus a2 e to the minus gamma t. We can just call the sum a1 plus a2 b e minus gamma t. And the problem here is that the solution is incomplete. So when you get to a case like this, remember you have to add a linearly independent function to the kernel. So we will add to the kernel, and you just do that by multiplying something you've got by t in this case. So we'll add to the kernel a term a t e to the minus gamma t. So our complete solution here is at e to the minus gamma t plus b e to the minus gamma t, like so. All right. So now let's go ahead and release from rest. So we'll be demanding that x dot at time 0. We're just going to set that equal to 0. All right, so in general, x dot of t is going to be, well, differentiating this is going to give me, well, first we'll differentiate the t, leaving behind an a e to the minus gamma t plus a t, and then we have to differentiate that. This can bring down a minus gamma, so it's a little fast there. So this will be minus gamma a t e to the minus gamma t. Then we're going to have a similar term here from the b, minus gamma b e to the minus gamma t. All right, and since we require that x dot at 0 will be set equal to 0, that means e to the minus gamma t, all the e to the minus gamma t's are 0 and t is 0 there, so I'm just left with a minus gamma b being set equal to 0. So that requires that my a be equal to gamma b. So with those initial conditions, my solution becomes x of t equals gamma bt e to the minus gamma t plus b e to the minus gamma t, and I can gather that a little cleaner. B times gamma t plus 1 e to the minus gamma t. All right, so what we've got is an exponential decay, but there's also this linear term too, but the exponent will win. So the upshot here is if I plot it out, I'll just use the same graph and do it in red. The linear bit will win for a little longer, maybe say down to there, and then we approach our asymptote faster. So we still have the spring winning here all the way up to there, the damping winning here. So this is the perfect balance between the spring bringing it to equilibrium as fast as possible, and then basically hitting the brakes as late as possible to get it returned back to its original place as quickly as possible. This is what you see when you look at the loading. If you look at the sticker on your car, that gives you the maximum weight that you can have in the car. Remember gamma here, if we go way back, both gamma and omega naught squared, which show up in the Q, inversely depend on m. So the value of the mass they give you is that for critical damping. If you're at anything less than that, you are underdamped. That's because the last thing they want for your ride is for you to go into critical damping. If you can imagine, or sorry, into underdamping. You can imagine what it's going to happen with underdamping. The spring's going to win too much, then you're going to hit the brakes too late. You're going to overshoot, and then it's going to try to return it, but you're going to hit the brakes too late, so you're going to overshoot, and it'll try to return it, and so forth. And that's the case we're going to develop next. Okay, so case 3, critical underdamping. All right, so in case of underdamping, remember we said that our Q is now imaginary. So that was equal to gamma squared minus omega naught squared, but in underdamping omega naught squared is bigger. So if we want, we can rewrite this as I times the square root of omega naught squared minus gamma squared. Just pulling in just pulling out a -1 out of the square root. Okay, let's give this a name. So this radical we'll call omega d for the damped angular frequency. Okay, so with that identification, our general solution, x of t equals a1 e to the minus gamma minus q t plus a2 e to the minus gamma plus q t. That's going to now become a1 e to the minus gamma minus I omega d t plus a2 e to the minus gamma plus I omega d t. All right. Now, for reasons that will make sense in a moment, I am going to rename a1 as C plus. Yeah, I know it's multiplying the thing with a minus there, bear with me. And a2 I'm going to call C minus. All right. So with that renaming, so x of t is now c plus times e to the minus gamma minus I omega d t plus c minus e to the minus gamma plus I omega d t. Okay. Well, the one thing that both of these terms have in common is an e to the minus gamma t, so let's pull it out. So e to the minus gamma t times c plus e to the plus I omega dt. Now you see why I chose it that way. Plus c minus e to the minus I omega dt. All right, now let's not forget that a physical observable has to be an element of the reals. So, since we're requiring that it be real, another way we can demand reality is to demand that the complex conjugate of t, x star, yeah, I know x star. If you've had complex variables in math class, they write it as x bar. The physics and the math community have never agreed on that notation. Physicists always call it x star. So we're going to demand that the complex conjugate of t be equal to t. The only way that can happen is if it's real. All right, so let's go ahead and do that then. So we're going to have e to the minus gamma t, that's real, so I don't have to conjugate that. C plus, I do have to conjugate that. Star, the conjugate of e to the minus I omega t is, e to the plus I omega t is e to the minus I omega dt. Similarly, plus c minus star, e to the plus I omega dt, and we are demanding that that equal e to the minus gamma t c plus e to the plus I omega dt plus c minus e to the minus I omega dt. Cancel, cancel for what that's worth. All right, now the big deal here is we need to compare coefficients. We have an e to the plus I omega t here and there, so that demands that these two terms be equal, and by the same token with the e to the minus I omega t there, that demands that that demands that that term and that term also be equal. So let's just go ahead and we'll look at the blue case first here, I think. No, look at the purple case first. So requiring C plus star equal to C minus, let's give that name C. Well, for the blue case, we can rewrite that as C plus equals C minus star equals, well, this is just the complex conjugate of that, that's the complex conjugate of that, so it's got to be the complex conjugate of C, whatever that is. All right, so with all that, we can rewrite our x of t as e to the minus gamma t times c star e to the I omega dt plus c e to the minus I omega, omega dt. All right. Now, with time, you will see this often enough that you'll just look at this and say, oh, I can write this as a sine function. And you'll kind of just mentally go straight there. But let's go there more slowly and carefully. At least this first time. So first off, what we're going to do is we're going to rewrite C in a way that will make complex conjugate taking a little easier. I can let my C equal some real a over 2 times e to the minus I theta naught. So by doing that, I've just taken a real, I've multiplied it by e to the minus I theta naught. That will give me any complex number I like with suitable choice of a and theta naught. Okay. So I can rewrite my x of t as e to the minus gamma t times a over 2 e to the I omega dt plus theta naught plus a over 2 e to the minus I omega dt plus minus from the complex conjugate minus theta naught. All right, that's all well and good. So to get into some sort of happy sines and cosines, let's go ahead and use Euler's identity. So just recall, you gotta love Euler. Euler and Gauss, between the two of them, if you forget the name of a theorem, you've probably got a 50% shot of getting it right if you guess one of them. Okay, so recall Euler's identity, e to the I theta equals cosine theta plus I sine theta. Awesome. All right, so then my x of t becomes a over 2 e to the minus gamma t, just pulling that out. All right, here we go. So we'll have cosine omega dt plus theta naught plus I sine omega dt plus theta naught plus cosine omega naught t plus theta naught. Oops, sorry, the cosine of the negative of that, but we'll see that doesn't matter in just a nanosecond or so, plus I times the sine of minus omega dt plus theta naught. Phew, okay. So now you remember the cosine of minus x is just x. So these two terms just add. And the sine of minus x is minus the sine of x, so these two terms actually cancel. Yay! That gets rid of the imaginary part that we don't like, given that we're looking at a physical observable. So I've just got two of these cosines adding together. That's why we made it a over 2 to begin with, to cancel that 2. So I now have a e to the minus gamma t cosine omega dt plus theta naught, but that's not how we usually write this. We usually like to write our simple harmonic oscillators as sine, but that's okay. If I just shift my initial phase by pi over 2, I can turn the cosine into a sine, and we're all happy. So I will rewrite as x of t equals a e to the minus gamma t sine omega dt plus phi naught, where phi naught differs from our theta naught by pi over 2, but at least gets it into the nice standard form. All right, so now if we go and look at what this looks like, so here's plus a, there's minus a. I look at the a e to the minus gamma t bit here, and I see decaying exponential. And since we're going to be oscillating, this is the amplitude at any given time for this oscillation happening. So I'll just kind of draw in a matching envelope over there. And then the actual motion is going to look something like that. So our oscillation is occurring within this decaying envelope. All right. So we are oscillating, though, with frequency omega d, which is not the natural frequency of the spring of the undamped spring. It is a little different, so we do need to compare that. So let's go ahead and compare omega d, omega damped, to omega undamped. Okay, we recall that omega damped was defined to be the square root of omega naught squared minus gamma squared. So what we have here is that omega damped is going to be less than omega naught. And so that means that the damped period will be greater than the undamped period. But typically, your values of gamma are pretty darn small compared to omega naught. So yeah, you might be able to measure, but it's not going to differ by much. All right, in the next video, we will go and take a look at the energy considerations.